All right, so we will review. This is 3.5, number 6. So again, 3.5 is just a review of all the techniques that we've gone over so far. Here I need to do some kind of a substitution. Thoughts?
U equals sine of x.
U equals the sine of x. Excellent. Right. So U is equal to the sine of x. And du is the cosine of x dx, which happens to be sitting right there. Ignoring the boundaries for a moment, I get 2e to the u du, whenever you write it. Antiderivative for e to the u,
E to the U.
e to the u. And u is really the sine of x, so switch black. So now we have 2e to the sine of x, and that's evaluated from 0 to pi over 2. So let's see, sine of pi over 2 is 1. All right, yeah. So I'm going to get 2 times e to the 1, which is e, and then sine of 0 is 0. E to the 0 is... Nope. 1. Yeah. So that would be my answer right there, 2e minus 2. Not too bad. Gotta pick the right u.
Let's see. No, never mind.
No, because this is a definite integral, right? So no plus c here. Just ends up with that. All right, that was pretty easy. All right, next one. Now the book said, the homework said to use the integral table, so we can look this up in the integral table. But let's try it out first. Let's see.
What number was this one?
Oh, sorry, this is number 11. So 3.5, number 11. Suggestions.
Can we rewrite the square root as x squared squared and then
Yes.
x squared is the u?
Yeah, so rewrite. I'm going to put the dx off to the side because it bothers me when it's in the numerator. And inside the square root, we have x squared squared plus 4. And so if we let u equal x squared, then du is 2x dx, which happens to be sitting up there. So our new integral is the integral of 1 over the square root of u squared plus, I'm going to call that 2 squared du. And so sometimes to use the tables, you got to do a substitution to make it look like what's in the tables. So we should be able to look this up in the table. Try it another way to confirm. So we have a lovely integral table. And we had a plus in the square root, correct? So I'm looking, I wonder if I can search. Which will let me do u squared? Oh, it doesn't like that.
Number 72.
72. Yep, that's the one right there. Yeah, so the answer should be just the natural log of the quantity u plus the square root of a squared plus u squared. So that should be my answer. Just grab that formula. Oops. And our u is x squared, so we could just jump right to an answer based on that. So back to black. So it did. Ooh, that was weird. Definitely time to ask for a new kind of device. Where am I? Natural log of u is x squared plus the square root of 4, it's my a squared, plus u squared, which would be x to the 4th. And we definitely need the plus c because we didn't have boundaries. So, what if we didn't have the table? What might we do? Trig substitution, yeah, so let's try trig substitution next, review that technique.
Are we going to have the table on the final?
Yes. But there will be some questions for which I say, show me how to do this with trig substitution. Right? But you'll know what the answer is based on the table, so hopefully you can fill in the, connect the dots there.
How long do you have to take the final?
2 hours.
Oh, what day is the final?
Thursday?
For the people in section 1, it is Thursday.
Can we take it before
For
Thursday?
the online people, the deadline is Wednesday. Yes, you need to schedule that.
Okay.
So I gotta double check on my schedule list. So. Yeah, so if anyone wants to take it before Thursday, which I highly recommend, so I have more time to grade it. Anyway, all right, trig substitution here. So in order to do a trig substitution here, I need to consider a triangle. Put my theta right there. So let's see. This has a plus in the square root, so that means the square root is my hypotenuse. So x to the 4th plus 4. And then the Pythagorean theorem says something got squared to give you each of these. So what was squared to give us 4?
2 and x.
2. So I'm going to put the 2 there. And what was squared to give x to the 4th?
X squared.
X squared, so the x squared is going to go over there. And remember I talked about before, you want to avoid having your x term on the adjacent side. So that's why I chose those 2 places to put them. Okay, the easiest function to make based on this would be the tangent, I think, right? Because that involves these 2. And so that's going to give me the tangent of theta is equal to x squared over 2, which you can rewrite as x squared equals twice the tangent of theta. Now we could have done a u substitution here and played with that u just like we did before, but we can just do it with the x squared. Let's see, what else do we need? We need a dx to do this. What's that? Well, we could do implicit differentiation. You don't remember implicit differentiation from way back? We did this last week. An example like this one here. What's that?
Take the derivative of both sides.
You take the derivative of both sides. Yeah.
Okay.
Okay. Now x here is a function of theta. Yeah. Okay. So on this left side here, what I get is ordered derivative of x squared normally would be 2x, but x is a function of theta, so I get a dx d theta. So there's more than one way to do this. I'll show a couple ways. On the other side, I'm taking the derivative with respect to theta. The derivative of the tangent is secant squared. Yep. So I'm going to get 2 secant squared theta on that side.
Can you solve for d?
So then I have to solve for dx, right? So I would say then dx, the 2's are going to divide out, which is kind of nice. And then I'm going to get a secant squared of theta divided by x d theta. Problem,
There's an x.
there's an x over there. Okay. Now, that's really not too much of a problem because I could just take that x and put it back where it was. And why can I do that here? Anybody?
Algebra.
Okay, algebra is one reason. Why would I bother doing that bit of algebra in this case? William?
We have an x in the top.
Yeah, we have an x dx right there. Yeah. Okay. If that wasn't there, I would have to resolve that x into a function of theta. How would I do that?
Just go back up.
Take the square root of that equation right there.
It would be a mess.
It would be a little bit of a mess, right? So the alternative to implicit differentiation here would be to rewrite that as x equals the square root of 2 tangent. And now do your differential. So then if I did it that way, I would say dx equals the derivative of a square root. Anybody recall what happens? 1 over twice the square root is what goes down there. So we'd have a over twice the square root of 2 tangent. And then I would have to take the derivative of the inside, which is 2 tangent. That would give me 2 secant squared. 2 secant squared of theta. Yeah. So that's the alternative way to do it. Okay, so we have a couple different options here. I think this one looks nicer at the moment, but both will in the end lead to the same result. So I like that substitution there. What's the square root equal to here, according to my triangle? So 2 divided by the square root would be cosine, which works out very nice here. So cosine of theta is equal to 2 over that square root, because I have 2 over the square root right there. That's cosine. I have x dx right there, which is secant squared of theta. I'm going to sneak in blue underneath. I believe this turns into the integral of the cosine of theta times the secant squared of theta. Secant is 1 over cosine. Yeah. So we now have cosine of theta times 1 over cosine squared, because it was a secant squared, which is secant in the end, because that's going to be a 1 over cosine.
You go back.
Yeah.
You get the cosine on the top.
So what is 2 divided by the square root equal to? It's exactly equal to cosine. Yeah, so we got lucky there. All right, so then this becomes now the secant of theta, d theta. And does anybody remember the antiderivative of secant? It's a weird one. It's a natural log of, this is one I didn't prove, I just said we're just going to use it because the proof's kind of weird. It's the natural log of the secant plus the tangent.
And we have to substitute back in.
So now we have to back substitute. So we got to look back at our triangle and say, okay, what is secant and what is tangent? So I'm just going to redraw my triangle right here to figure that out. There's theta. There's the square roots. Oops, this used to be next to the fourth. And let's see, that's an x squared. That's a 4. Is that right?
2.
No, it's a 2. Yeah. All right. So tangent is x squared over 2. Yeah. And secant is, let's see, cosine is 2 over the square root, so secant is the square root over 2. So I get the square root of x to the 4th plus 4 over 2. Those two are added together, they're inside the natural log. So we have an answer. Does that match the answer we got before?
No, there's a plus 2 on the bottom.
Oh shit, it doesn't match. Did we mess up? What's that? Yeah, so I'm going to show you how the plus c plays into this. Okay. So the table said the answer should be x squared plus the square root. Now we have a divide by 2 in each of those. So This is a black C right there. It's probably not the same as our red C on the other page. Okay, so maybe I'll call this one C1. And then over here, we'll call this one C2. So what I'm going to show is that they're not going to be the same constant. All right, so check out this natural log here. Another way to write that, because they're both divided by 2, is I have the square root of x to the 4th plus 4 plus x squared all over 2. And then what happens if you have the natural log of a quotient? The rule?
Subtract.
It turns into a subtraction. So this becomes the natural log of the square root of x to the 4th plus 4 plus x squared outside the roots, and then minus the natural log of 2. And what can you tell me about the natural log of 2? It exists, it's just a constant. So this is the different constant. So remember we had a plus C2 here. So if we wanted to reconcile the two ones, well, the C1 from the formula in the book is really whatever RC2 is minus the natural log of 2. The bottom line is any two antiderivatives can differ by a constant. These two antiderivatives differ by a constant. The difference is the negative natural log of 2. It happens. You use two different techniques, you get slightly different answers. But they're just graphically vertical shifts of each other. Same shape graph. Okay, let us try. Let's see, those are the two problems we were looking at for the homework. All right, we're going to move on to something new.
This is the option section.
No, I'm going to skip over that for now, and I'll do an example from that. And the only reason I'm going to do an example from the optional section is because it reviews Riemann sums, which is going to be on the final. Yeah. So we'll do a couple of examples of that tomorrow. We're going to jump into the section after that, which is, what number would that be? 3.7, improper integrals. So what does it mean for an integral to be improper? All right, so 3.7 improper integrals. So we've been doing all kinds of integrals. This is called a definite integral, right? Because it has boundaries on it. And the conditions on f of x that allowed us to turn a Riemann sum into an integral, we want f of x to be continuous on the interval from a to b. And guess what a and b are? Numbers. They're numbers, yeah. A and b, so are real numbers. You turns out you can integrate with imaginary numbers, but it's a little wild. So that comes up in a course called complex analysis, if you ever take that. And the only people that really take that are people that want to major in math. And when they're majoring in math, that's true. Yeah. So engineering people usually don't take that. Oh, unless you're going into like signal analysis, like radio waves, radar waves, and things like that. Electrical engineering might need to take that. But it might be, they might just stuff that information into an electrical engineering course instead of a math course. So A and B are real numbers for us. So these are the assumptions that we've been working on since we started this course. So an integral is improper if it breaks one of those rules. What are the two rules? Well, it's got to be continuous, and A and B are real numbers. Okay? As long as we don't break those rules, it's proper. If we break those rules, they're improper. Well, okay, let's see. So to break it, I would have to have a discontinuous function, or A and B won't be real. For us, not being real, the alternative is infinity or negative infinity. We're not going to jump into the i's, right? That's a whole other thing, but that's a different branch of calculus that we're not going to get to. So, and as far as the not continuous, just little breaks in a function, like if the function was like that, and then it jumps up here and continues, that's no big whoop. That's super easy to integrate across. Okay. The problems are going to happen if the function, ooh, my slides are out of order,
Yeah, they are.
or did I hit the wrong button?
Or, no, you hit the wrong button.
I hit the wrong button. Ah, here we go, thank you, Sarah.
Mm-hmm.
So the problem is going to occur for us if, let's say, a function has a vertical asymptote, something like that. Can we jump across its vertical asymptote through integration?
No.
Maybe.
Maybe.
Just split it.
Oh
Yeah.
dear.
Yeah, so we can try and split it up, okay? So this could be a picture of f of x equals x squared. So maybe I try to integrate from -1 to 1. Oh, sorry, 1 over x squared, excuse me. Dx. So the problem is this is discontinuous at 0, so you gotta break there. You gotta separate the two areas. So that means I want to consider the integral from -1 to 0 of 1 over x squared dx, and then I'd want to consider the integral from 0 to 1 of 1 over x squared dx. Now, other things that can help me out here is this function is even symmetric, which means it's symmetric about the y-axis. So that means this integral is going to have the same value as that integral. So in this case, because of what's called even symmetry, I can say this is twice the integral, and I can pick which one I want. I want the right one, because it doesn't have negative numbers in it. So again, we can't always do this, but sometimes we can. All right, so I got a slight problem though, because
From the 0, is it?
the 0 is kind of a problem. So I'll show you how to deal with that next. So I have this new integral I want to deal with. It's the integral as x goes from 0 to 1 of 1 over x squared dx. Now, ignoring the boundaries for a minute, you guys can give me an antiderivative here, right? This is x to the -2 power. So the antiderivative is, so again, we're integrating x to the -2 dx. I got a couple different answers there.
It's,
Add 1, right?
yeah.
So x to the -1.
Over x.
Negative 1 over x.
1 over negative.
And it's going to be negative. Yeah. So this is what I have next, which we can write as 1 over x, but negative. And the problem here is, oh, I can't just plug in 0. Okay. So what you do instead with improper integrals is you introduce a new variable. Let's use b. Let's let b equal 0. Eventually. Okay. So now what I'm going to do is I'm going to say, all right, let's take -1 over x and evaluate it from 1 to b, or from b to 1. No problem. That gives me, let's see, -1 over 1 minus -1 over b. Clean up the signs a little bit, and I get what? -1 equals -1 plus 1 over b. And I have a sign error somewhere.
You don't have a sign error.
I do have a sign error somewhere. I'll show you why in just a minute. Okay, let's continue with what we have here. Now, we can't just plug in 0 because that's illegal, so what we have to do is take a limit. So, crank this just a little bit, move it up. So now I take the limit as b goes to 0 of this expression, -1 plus 1 over b. And what happens to 1 over b as b goes to 0? Well, I don't have an error. This works right. As b goes to 0.
It doesn't exist.
It's 0. It goes to.
It goes to infinity. Yeah. So this gives me -1 plus infinity, which is infinity. So in this case, there is no answer.
Oh, lovely.
So what does this tell me? It tells me that, let's get a better graph from GeoGebra. If we look at the graph of 1 over x squared, that in this region from 1 on up, there's an infinite amount of area as we go up forever. Is it always going to be infinite as we go up forever?
Did you say something?
Answer is no. What's that?
Did you say something counter to that before?
I think there's a volume.
Oh, that was a different problem. Yeah, so it depends on the problem. Every problem is different. That's why we got to go through all these steps to kind of figure, does this one explode or does it settle down?
Well, if we're dealing with asymptotes, isn't it always going to be infinite?
No. So I'll give you another example. No. So, similar problem. Let's look at the integral as x goes from 1 to infinity of 1 over x squared dx. Okay. So now what I'm doing, if we look back at that picture from GeoGebra, I'm saying, okay, let's start here, and then we're looking at the area between the curve and the x-axis. As we go out forever, is there going to be an infinite amount of area underneath, or does this thing sink down close enough to the axis to have a finite amount of area? Turns out that's possible. So again, kind of zoomed in on this. This function has the point 1, 1, and then it heads down with an asymptote like that. And what we're wondering is that, is it possible that there's a finite amount of area under there, or like the other side, does it explode to infinity? So the trick is you rewrite this.
Here's the highlighter.
She's got good eyes, she's sharp.
It's like magic. Fill on the highlighter.
Ah! Okay. So what I do is I rewrite this. Okay, let's take the limit as b goes to infinity of the integral as x goes from 1 to b. So we let b be a placeholder until we're ready to take the limit. And then we clean up the antiderivative. All right, so we know that the derivative of this, the antiderivative, sorry, is negative 1 over x. So now I want to know what's the limit. The limit's in there as x goes, b goes to infinity of negative 1 over x as we go from 1 to b. Okay, so we plug in limit b goes to infinity of, let's see, we plug in a b and I get negative 1 over b minus negative 1 over 1, which is a plus 1. I'm just going to change the order. Limit as b goes to infinity of 1 minus 1 over b. And what happens as b goes to infinity this time? Nope. 1 over a really big number
Is a
is a really small number.
It
goes to 0. Yeah. So it turns out in the limit, that fraction goes to 0. And so it turns out there is a finite amount of area under that curve, even though we're going to the right forever looking for area. It just, this thing crashes down toward the axis fast enough to have a finite amount of area as we move out there. Okay. So here's a different way to think about it. So an integral is an area function, correct?
Yes.
Okay. So I'm going to say my area function for x is the integral from 1 to x of 1 over x. I'm going to use a different variable now because I used x for something else. 1 over t squared dt. Right. This area function right here describes me finding this area up to any point we call x. Okay. So we actually finished that. What we found based on our work here is that this area function is equal to 1 minus 1 over x. So if you said, can you find me the area under that curve from 1 to 2? That would be a of 2 according to this function. Well, that would just be 1 minus 1/2, which is 1/2. Graphically, what did we just find? Well, here's the point 1, 1. We went over to 2. If you square 2, you get 4. So then, oops, sorry. We just found that area right there. It's 1/2.
Wouldn't it be 1 over x minus 1? Because
So I just reordered things here. So over here, this right here is going to end up being a +1.
oh,
And so I just wrote that +1 first, and then I wrote the -1 over b second. Okay. Suppose you wanted to find the area from 1 to 100. What would that be equal to? 1 minus 1 over 100, which is 99 over 100. What if I asked to find the area from 1 to 1,000?
0.999.
0.999. What if I wanted to find the area from 1 to 1,000,000?
Leave it in close.
0.99999. What if I wanted to go from 1 to a billion, billion, trillion, quadrillion? 0.99999999999. The limit of that sequence of nines is 1. Yeah. Isn't that bizarro?
Yeah.
Yeah. So sometimes the limits blow up. Sometimes they converge to a particular number. Okay, like in this case, 0.9999999, which eventually is, we're pretty close to 1. Will we ever go over 1?
No.
No, we won't, because we're always, if we don't get to infinity, we're always missing a little bitty chunk out there at the end. Just a little tiny, even though that tail is infinitely long, there's only a little tiny bit of area hanging out in there, no matter how long it is. It's weird.
So that's like with the bucket problems when the rope was a negligible weight,
Yeah.
how it's just so small that we just don't count it.
It's just so small we don't even bother counting it. Yeah. The rounding error is insignificant. Yeah, that's another thing. All right, let's try another one. So I'm going to do a slightly easier function and see if we can figure it out. So consider the function 1 over x. And let's go from 1 to infinity. Okay. Now, we can't plug in infinity because it's not a number, which means we need to involve a limit. So we need to take the limit as b goes to infinity of the integral from 1 to b. So usually what I do is I ignore the limit for a little while and I just clean up that. So let's just worry about that. So ignoring the limit, what's an antiderivative for 1 over x? So we've got the natural log of the absolute value of x. And we need to evaluate that from 1 to b. Okay, no problem. Now, by the way, b is to the right, is my assumption here, right? Why? Because I'm heading to positive infinity, which means I really don't need absolute value here anymore. So this becomes the natural log of b minus the natural log of 1. What's the natural log of 1? Get away from your calculator.
This is 0.
So this, it's 0, yeah. This says e to what power equals 1, and it would be the power 0. Because a natural log spits out an exponent for base e. Yeah, so this is just equal to the natural log of b. Okay. So now what we want to do is, what is the limit as b gets big of the natural log of b? Do you remember what the natural log function looks like? So e to the x looks like that. And natural log is the inverse of that. The inverse is a flip about, whoa, what did I do?
Oh, you made the.
I accidentally grabbed that and moved it.
Yeah.
I moved back. Oh, all right. So, try it again. The inverse function is the natural log. It's a flip around the line y equals x. So if that's e to the x, then the natural log of x looks like that. So whereas e to the x has a horizontal asymptote, natural log has a vertical asymptote sitting right there. But just like the exponential function goes up and to the right forever,
So also.
the natural log goes up and to the right forever. Now it grows very slowly. If you look way out on the natural log, you'll see it's not climbing very fast, but it is always climbing. It is always climbing. So this
So that when we
grows without bound, which we're going to call infinity. So is there a finite amount of area under 1 over x? The answer is no, there is not. What about 1 over x squared?
Yes.
Yeah, that one shrunk down quick enough. That one shrunk down quick enough. So sometimes these things converge, sometimes they don't. The only way to know is to find an antiderivative and then at the trouble point, do a limit. Right? And that's what improper integrals are. It's when we break the continuous rule or we break the rule that the endpoint is a real number. And the way we break that is by saying, hey, well, what happens if infinity is involved? And sometimes interesting things happen, and sometimes it's not so interesting. It's like, hey, yeah, it's infinite. Of course it's infinite. We went out to the right forever. But other times, even though we go out to the right forever, it's finite. Isn't that nuts? Math is so weird. There's so many bizarre things in it. All right, so we have enough time for one more example. Let's pull something out of your homework. Let's see. This is 3-7.
Number 7.
Number 7 looks exciting?
Yeah.
Wait, did you actually do the homework?
No.
A little bit. Oh.
I know.
Okay.
I know you're gonna be really impressed, right?
Oh yeah, this is a good one.
No.
All right, so let me steal this. Yes, sir.
Going over 3.6 or
So 3.6 is optional extra credit. And so I'm going to do a couple of examples from it tomorrow, mainly because it reviews Riemann sums, which are going to be on the test. But the direct content from 3.6 will not be on the final. Okay. So basically, where we were doing Riemann sums with just right-hand endpoints before, section 6 says, okay, well, let's look back at midpoint again. And then it shows what's called the trapezoidal rule and what's called Simpson's rule, which is to try and fit a parabola on top of each group of 2.
Do we need any of that stuff for calculus 3?
I don't think so.
Okay, perfect.
So feel free to tune out that day if you wish. But I am reviewing Riemann sums as part of it. Okay, so we'll do that tomorrow. Over pizza and pie, because it's pie day tomorrow.
7.
So this is 3-7, number 7. And the problem here is that this function is undefined at 7. There's a vertical asymptote there. If we were to look at the graph of it, which is not a bad idea. Desmos, oops, too much. F of x equals, what was in the top?
9.
9 divided by
The cube root.
parentheses
X minus 7.
x minus 7 raised to the power 1/3. All right. And rescale so we can see this better. So then if I go in here and I graph x equals 7, we can see that is the vertical asymptote for this function. So we're going to have to, we can't just plug in 7 because that's going to be a problem. So we're going to have to take a limit after we get an antiderivative. So what we're going to do is we're going to rewrite this. And what we're going to do is we're going to go from b to 9. And then after we'll take the limit as b goes to 7. So let's see, we have, I'm going to rewrite it as 9 times x minus 7 to the power negative 1/3. So since this isn't a 2x in here, it's just x minus 7, I don't have to do a u substitution. I can get away without doing one. What's an antiderivative for the power negative 1/3? We add 1 to it, right? So that's going to become 2/3. So the 9 is hanging out. We're going to have an x minus 7 to the 2/3, and then we have to squeeze in here a times 3/2, right? Because we divide by 2/3, which gives me a times 3/2. And I want to evaluate that from b to 9. So 9's not too bad. I just have then, so 9 times 3 is 27 halves. I'm just going to pull that out front. And then, let's see, 9 minus 7 is 2, so I have 2 to the power 2/3. And, 2 to the 2/3, 2 isn't the perfect cube, so it's just 2 to the 2/3. Don't bother plugging that in the calculator yet. And then we have to do a minus, plug in the b. Now, just note here, I did pull out the constant here. So I'm ignoring that in the parentheses for now. So then I just have b minus 7 in parentheses to the power 2/3. And now I'm ready to take the limit to see what happens. So I want to know what's the limit of this thing. So the limit as b goes to, in this case, 7 of 27/2 times 2 to the 2/3 minus parentheses b minus 7 raised to the power 2/3. All right, so the next thing to consider is what's happening here. Well, the 27/2 is just a constant, so the limit passes through that into this difference here. You can separate this into the limit of each part of the difference as long as both limits exist. Well, there is no b here, so that limit certainly exists. So really, I'm just worried about what's the limit of that single part as b goes to 7.
Can't
Well,
plug 7 in.
You can always cheat and plug it in and see what happens. If something weird happens, then you got to numerically evaluate it. But if I cheat and plug in 7 there, what's 7 minus 7?
0.
Does 0 to the 2/3 exist?
It's just 0.
It's just 0. Yeah, 0 to the 2/3 is just 0.
So it's
Now, if that was the negative 2/3 power, then I would have a problem because that would put the 0 in the denominator. But this is just 0 to the 2/3. That's okay.
Okay.
So it turns out that in the limit here, color, this part right there, as b goes to 7, that just goes to 0. So what's left is everything else. So I have then 27/2 times 2 to the 2/3. That's the limit.
Whatever that number
So
is.
And this probably accepts exact same answer, so I could probably just type that right in.
So why were we focusing on b and not a?
Why was I focusing on this number, not that number? Because I looked over here and I noticed that the x minus 7, if I let x equal 7, I'll have a 0 in the denominator. So I looked at the graph to double check that. And when I looked at the graph, I could see there was a vertical asymptote at x equals 7. So that's why I picked on that number. Yeah, so you gotta, if infinity is involved directly, if it's not one of the endpoints, then you have to look to see if there's a break in the function in the range you're looking at. And the break could be at one of the endpoints, but it could be in the middle somewhere. So the first example I gave, the break was in the middle, so I had to separate around that break and do a limit. In this case, the break was at the beginning, so I replaced the beginning number with a b, and then took the limit after I closed that.
And then we would still have to take this, we still have to.
We're done.
Integral from 9.
We did the
to
integral. No, we did that,
Okay,
right? Because we found an antiderivative,
yeah,
and then
we
we plugged in our 9 right
yes,
there.
yes.
Yeah, so this right here says, give me a b that's somewhere between 7 and 9, and this will tell you what the area is.
Got it.
Yeah. What's up?
Shouldn't. Wait, no.
Yeah, so I'm just going to plug this into the computer and just get a check mark, even though it doesn't really save it for me because I'm the teacher. So I believe the answer is, it says enter a mathematical expression, so I can just type 27/2 times 2 raised to the power, parentheses, is 2/3, right?
Yeah.
And yeah, that looks like what I typed. I don't get a syntax error. And I got it right. On the first try. That happens sometimes. Oh, yeah.
So are we gonna actually do limit rules? Or is
I'm going to go over more of these tomorrow.
Okay.
Yeah, so tomorrow I'm going to do more of these, and then I'll do some examples of numerical techniques, which reviews Renaissance science.
okay, and then are you going to class test or take home?
Probably take home.
Well, when do we get the take-home test?
Try to do
I
it.
think I said I would give it. I think I sent out a note that said I was going to get it out tomorrow.
Yes.
Tomorrow?
So is that all you're doing then today?
What's that?
Yeah, I'm kidding.
I think that's what I said in the email. I said tomorrow. It did say Thursday. Okay. Yeah, that's what I thought. So I'm still working on it, getting there, almost done. Tomorrow is Thursday, yes, I'm free before class. And then after class, but after class is pi day, so you have to discuss math between y and pi. If you haven't had enough pi in class. 'Cause we'll have pi in
Still
class,
lose.
too. Okay, well, we're gonna do more tomorrow, so don't worry, we'll keep working on it.
Oh.
I just need to kind of review that assignment I'm doing.
Yeah.
Sure. Make sure I've got good notation.
Okay.
I finished it up last night.
Oh, cool.
I just need to clean it up.
And the command started working again after that?
Well, I basically had to just reboot computer, reload everything, just basically start off. And then it just kind of went smoothly. But he resent out that instruction sheet because some other student found the error.
The minus is missing?
Right, that's another error. So I emailed him about the minus and the codes. He resent out the whole thing, so that was good code.
Yeah. Good. Okay.
Thanks.
Yeah.
Stop broadcast. Oops.